So we'll look at the same data set as before, and I'll use a mixed model. This is similar to an analysis of variance or a general linear model, but the main difference is that when you've got repeated measures data, it can model the correlations between the repeated measurements in a more sophisticated way and account for them in the model. So our main question, though, will be, do the treatments differ in terms of the signal measured? So first of all, this is some prop mixed code with the sort of fairly standard settings. This class variable sort of statement comes in a lot of procedures. It's really something to specify which of the categorical variables. And here our categories are going to be the time effect, the sample ID, and the treatment effect. We set up the model, so we simply say the thing we want to analyse, which is signal, the fixed effects in the model that we want to fit, a time treatment, the time by treatment interaction with a star used to sort of say this is an interaction. This repeated statement simply gives us a structure for the repeated measurements. It says it's structured over the time effect. Observations are repeated within the sample ID, and this is the structure for their correlations, which here is just going to be a constant correlation. And you fit that model, and it gives you fairly standard output to start with. It just tells you what your classes were, which is quite handy to see, how many observations that it has in the data set, how many it actually used and didn't use. And then you'll see a table which is fairly similar to an analysis of variance table with an F-test for each of the fixed effects fitted, which here are each highly significant. So we've got a highly significant interaction between the time and the treatment effect. So we've shown that the treatments are different. We've shown that the treatment effect differs across the time points, but we haven't really got any statistics out telling us which treatments differ. So we do need to go on and do a bit more. So one thing that's useful is to get the means for each treatment. We can do that using this by adding this ls means statement. Here it's just giving us the overall mean across all the time points, and the estimate is the overall mean. So you can add that in if you would find it useful. You probably want to get the differences between the overall treatment means, so you could add in this diff option to the ls means statement, and then you get the differences between each of the pairs of means. As I said, anything you get out of SAS you can output to a new data set, so it might be helpful to get these differences between the treatment means into a new data set and then present it in a nicer way in a table. So there's a statement that you can use with a lot of the procedures, this ODS output statement. ODS stands for Output Delivery System, and you would specify that you want to put the differences into a new data set which we'll call differences. And then you can go on to do a proc tabulate using this data set. So we say we're going to use that data set called differences, and we'll do a table just as similar way to before. And this time we're going to get the means of the estimates and their confidence intervals. So these are the differences in the means with confidence intervals relating to that analysis, and now we've got it presented a bit more nicely in a table. By default, you normally use 95% confidence intervals. If there was a situation where you wanted wider confidence intervals to give you greater confidence about the interval within which the true value lies, then you can change that to something like 99% confidence intervals using this alpha option. SAS thinks out its procedures very carefully. There's normally an option for anything you might want to do in there somewhere.